What's going on, everybody? Well, you have been in the process of learning two very, very important identities when it comes to the use of trigonometry. And that is that although these trigonometric functions are originally born out of a study of specifically right triangles, we come up across two identities that apply not only to right triangles, but to all triangles. The first one was the law of sines, and today we finish it up with the second of the two, the law of cosines. So as we take a look at this here, we're going to be working with that um, and learning it today. So let's first of all take a look at some warm-up problems here. I want you to work with these. There are three warm-up problems here. Now these are not in your workbook here, but I'd like you to take a look at them and to ask yourself if you can come up with some answers on this. Here's the first question. For any right triangle, solve the Pythagorean theorem for c squared, make that c squared, and then also solve it for a squared. Those two things there. So solve it for c squared and solve it for a squared. That's not going to be too difficult to do, especially for c squared. The second one here is cosine positive or negative in the first quadrant, and is cosine positive or negative in the second quadrant. Ask those two questions there. Those will be very, very quick questions. But more importantly, I have this last question here for you. I've given you two triangles here, one with three sides that are given, but no angles that are given. The other one with two sides given and the angle in between them also given, but nothing else. What you will find with these two triangles is that you cannot use the law of sines to solve those two triangles. Specifically, these are two instances, side, 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 and side angle side. And as it turns out, we need something to be able to help us calculate some angles for these things. And as it turns out, we need the law of cosines to be able to work with that. But I want you to convince yourself as to why you need something other than the law of sines to be able to solve these two triangles. Why is it that you cannot solve these two things using the law of sines? Take a look at those two things. You might have to pause the video here as you're looking at both of these, but take some time for this, and I'll see you in just a moment. Welcome back. Well, hopefully this was a pretty straightforward question, at least for those first two questions there. The third question is a little bit more involved in here, but we'll talk about it just a little bit more. So here's the first question here. If we take a look at, for any right triangle, solve the Pythagorean theorem for c squared and then also for a squared. Well, that's pretty straightforward here. It's given in terms of being solved for c squared here. And then if you solve it for a squared, you get something like this. I'm just giving this to you as a reminder that one is plus, and since you're solving for a squared here, this one is not plus, this one's minus. That's going to be important to know when we take a look at the law of cosines here in just a second. Is cosine positive or negative in the first quadrant? It's positive in the first quadrant. In the second quadrant, it's negative. And so that's what that is there. And if we take a look at these two triangles here, let me turn myself off here so you can see this. If we take a look at these two triangles here, and we try to set up the law of sines for each one of these. For the first one here, I've got sine of A over 19 equals sine of B over 14 equals sine of C over 8. And if I try to use this to try and solve for one of these angles here, A, B, and C, I can't seem to do it without having two variables in the equation. In order for me to solve it, I need to have basically only one variable in the equation to solve for. And so usually, in this case, in order to use the law of sines, you really need to have some combination of angle and side that are both known. If we have this side here, we also need to have this angle here, or some other combination of angle and side, both known, or some other combination of angle and side, both known. And if we have that, then yeah, we can use the law of sines. But since we don't have that, we have three sides and no angles, we cannot use the law of sines to be able to find out what any of these angles are. We run into a similar situation here when we have really side angle side, this kind of situation here. We've got sine of 45 degrees over A is equal to sine of B over 240. And sine of b over 240 equals sine c over 60. There's no way in which I can manipulate this so I'm working with only one variable to solve for. It's always the case that I've got two variables here. So this is an instance in which we really need to have another tool at our disposal to be able to solve for preferably one of those angles. Usually it's an angle that we're solving this for. Okay, so that's what the law of cosines is meant to really help us out here. So we're going to work with the law of cosines to find unknown sides and angles of triangles. There's also something else I'm going to show you here. This is called Heron's formula. It's another tool in your toolbox that you can have for finding the area of a triangle. You're going to have so many different formulas for finding areas of triangles. It's just going to be obscene. And then you're going to use this to solve some application problems here as well. All right, let's first of all derive what this law of cosines is here, and I've actually shown it to you a little bit in class before today, and so you've seen it a little bit here. I'm going to show you basically how we come across it, and I'm going to take just a regular scaling triangle here, one that we don't know anything about, certainly don't know if any angles are right angles or if any sides are equal or whatever. But I'm going to take this triangle here and I'm going to drop what's called an altitude from one of the angles here to the other side. And it's going to it's going to intersect that other side at a right angle here. And we're going to define this side here as being H. This dotted line as being H. So we started off with sides A, B, and C. We now have H here as well. And H touches side B right here. And so this divides side B into two parts here. That's D, that's here from here to here. And then we have side E here, which is from here to here. Okay, so let's see if we can come up with some some known trigonometric relationships, seeing as though this dotted line has created two right triangles out of our arbitrary triangle. So let's start off here with doing that. What are some trigonometric relationships that involve H that we can list here? Well, here's one. If we take a look at side A, the sine of angle A, opposite over hypotenuse, is going to be H over C. H over C, there it is. And because of that, we can solve that for H by making H equal to C sine of A. We're just multiplying both sides by C. The cosine of A is going to be this side D, not B, because D only extends out to this point right in here. That's the actual side of the right triangle. So it's D over C, and so we can use that to come up with an equation for D here as well. That's C cosine A. In addition to this, we can say that we can find E by taking the full side B and subtracting D. So that means, and since we have an equation here for D, that becomes B minus C cosine A. Okay. In addition to this, we can also, since this right in here is a right triangle, we can say that A squared is equal to H squared plus E squared. And we can keep A squared the same, make A squared, plug in C sine of A in for H, and that becomes C squared sine squared of A. And then plug in this expression here for E and square it, and that becomes B minus C cosine A, the whole thing squared. Okay. And the rest of really here is just algebra. What we do now is we can expand this out through FOIL. This becomes B squared minus 2BC cosine A plus C squared cosine A. And notice now we're going to have some things that we can combine together. We have a C squared sine squared A and a C squared cosine squared A. So if I factor out a C squared from each one of those things, then what I'm going to have in parentheses is sine squared plus cosine squared. And what does that become? You're going to see it here, C squared times sine squared A plus cosine squared A. We've just combined those two terms together and factored out a C squared. And what does this become here? Let me turn myself off here. That's just 1. And so this just becomes a squared is equal to b squared plus c squared minus 2bc cosine a. So we come upon something that looks an awful lot like the Pythagorean theorem, but it works for any triangle, any triangle, any triangle. And it's cool because there are actually three different versions of this here. And let's take a look at just what these look like here. You have a formula for a squared. You have a formula for b squared. You have a formula for c squared. And they all really look the same. Notice that unlike when you solved the Pythagorean theorem for a squared and you got minuses on a minus on the other side here, that doesn't happen with the law of cosines. It's always a plus sitting here. So a squared is equal to the sum of the squares of the other two sides minus 2bc. These are the same sides here, b squared plus c squared. So, and these are the same ones here. And cosine of a. Notice that for each of these three here, we have all three letters represented. If we're using sides, if we're solving for side A, we use sides B and C as well as angle A. If we're solving for side B, we use sides A and C and then angle B. If we're solving for side C, we use sides A and B and angle C. Hopefully you can see the pattern between all three of these here. So really, if you memorize one of them, or perhaps more helpful, write one down on your cheat sheet. More specifically, you'll see the pattern in all three of them here. And maybe you can write down all three versions. Maybe you don't need to do that. Maybe you can see the pattern and that's enough. Okay, so we can use this now to find the three angles in the triangle shown. Actually, we just need to use it once, because once we have one of those three angles, we can go back to using the law of sines, which is a little bit easier to find one of the other angles, and then the third angle, we just subtract the other two from 180 and we're there. So let's focus on the largest angle A right here, and let's make use of the version of the law of cosines that involves the cosine of the angle A, since we're trying to find the angle A here. Well, the thing is we want to solve this for cosine of A. Okay, so that involves bringing this to the other side and bringing a squared to the other side. And so it's going to look like this. Cosine A is equal to b squared plus c squared minus a squared. We also have to divide off this 2bc out in front here. And so that is why that's in the denominator there. All right, we can just plug stuff in. We know all three sides, and that's all we have to know in order to find out what cosine A is. Interestingly enough, we can find out, unlike with the law of sines, where you have to consider both possibilities, quadrant 1, quadrant 2, here with cosine, cosine tells you which quadrant you're in. This is an oblique angle. This is not an acute angle. The cosine is negative, so it's got to be greater than 90 degrees here. We're in the second quadrant. More specifically, angle A is 116.8 degrees. Okay. Notice, in order to find the next angle, we can just use the law of sines here. This is the law of sines. Sine of B over 14 is equal to the sine of angle A, which we just found, over side of A. And once we do that, then, oops, there we go. We can find out what sine of B is, which is that, and B is 41.1 degrees. And if we've got two angles, we can find the third one very easily by subtracting those two from 180, and we have our third angle. Hence, we've solved the triangle. All right, so I'm going to give you this problem very much like this one. It's find the three angles of the triangle whose sides have these three lengths here, 6, 8, and 12. A, B, and C, you have to find all three angles there. So take some time for that, and we'll be back in just a few minutes. Pause the video if you would, please. Welcome back. Well, hopefully this was pretty straightforward given what we've just gone through here. You've got three sides that you're working with. You only have to use the law of cosines once, and then the rest is familiar territory here. So let's take a look at this. We start off That's where we are here. I'm using this version of the law of cosines. Maybe you used one of the other two. It depends on which angle you were solving for first. Here I'm solving for angle C first. And so I get this. And interestingly enough, I find that this cosine is negative, and so I've actually got an oblique angle that I'm working with here. This angle is 117.28 degrees. For sine of A, to find angle A, I'm using the law of sines. And I get sine of A being equal to 0.444. And so angle A here is 26.38 degrees. Now let's just subtract both of those from 180, and I get 36.34 degrees. Now, there's kind of an important extra bonus lesson that comes out of this. It's usually a good idea to go for the largest angle first, because then that will give you an indication as to whether or not this is an acute triangle or an oblique triangle here. If the largest angle is still less than 90, then you know all three of them are less than 90. If the largest angle is oblique, you know that's the only oblique angle, because you can only have one oblique angle in any triangle. So let's look at this here. How do you know which angle is the biggest? Very easy. You just have to take a look at the sides. The largest angle will be opposite the largest side. The smallest angle will be opposite the smallest side. And the middle angle will be opposite the middle side here. So if you want to know which one to check as far as which one is oblique or not, we would want to go with angle C for this. Okay, so once again, how much information is enough when we're putting these kinds of things together here? Let's take a look at this particular triangle here where we know two sides. We also know the angle in between them. This is not side-side angle, because side-side angle would be one of these other two angles here. Side angle side means that the angle is in between the other two sides here. So this angle is in between these two sides here. This is not side-side angle. This is side angle side. And we're going to use this formula here. Notice that this is another instance in which you cannot use the law of sines to be able to solve this triangle here. This is the other example from the warm-up. So let's see if we can use this to find actually side B. If I can solve for side B, then I've got a combination pair here of angle B and side B, which will be enough for me to solve for everything else using the law of sines. So let's solve this for B squared. When we do that, we plug everything in here and we get 5.4 meters. All right, so we know that side B here is 5.4 meters. We can then use the law of sines here to be able to solve for angle A. And that gives us 69.7 degrees. And lastly, we can find out what angle C is by subtracting those two from 180, and we get 85.3 degrees. So just like before, we only have to use the law of cosines once to find one of the angles or one of the sides to make it so that we have a pair. Angle B, side B, angle A, side A, angle C, side B. If you've got a pair of those and at least one piece of information for everything else, then you can use the law of sines to solve for everything else. All right, so here's another one here. Given angle A, side B, and side C. Now, if you were to draw that out as a triangle, then you'd have to place angle A in between these two sides. So this is side angle side for this. So if you're given a triangle with these measurements here, find the remaining angles and side of the triangle. Take some time for that. Please pause the video. I'll be back in a few moments. Welcome back. Well, there was probably a couple of different ways in which you could use the law of cosines for this. I'm going to show you the way in which I did. So here I'm solving for side A, and I'm using side A squared is equal to B squared plus C squared. Again, this is always plus in here, always plus. B squared plus C squared minus, this is always minus, 2bc cosine A. And if I plug in everything that I need to plug in here, I get this value here for A. So I know um, side A. I know all three of the sides now, and I have a combination with me. I have angle A and side A, so that I can now use the law of sines to be able to solve for everything else. I'm using this to solve for angle B here, which turns out to be 59.4 degrees, and we can subtract all angles from 180 to find out what the third angle is, and that's 40.6 degrees. We've solved the triangle once again. Okay, so here's some applications here. We're taking a look at a pitcher's mound here, and we are not assuming that the pitcher's mound is located exactly in the center of the baseball diamond here. We allow it to be a little bit set back a bit, which I think is actually true. Um, Having said that, this is an angle here that's 45 degrees. The distance to the first base here is 60 feet. The distance to the pitcher's mound is 43 feet. And we have this third side here, H. So 60 feet, 60 feet, 60 feet, 60 feet for every part of the baseball diamond. But here's the problem that we're given here. The pitcher's mound on a women's softball field is 43 feet from home plate, and the distance between the bases is 60 feet, as shown in the figure. So how far is the pitcher's mound from first base? In other words, how big is side H here? So let's see what we've got here as far as information. We have a side, and we have another side, and we have the angle in between them. We don't have anything else to go off of here. We've got side, angle, side. Side, angle, side requires the use of the law of cosines for us to be able to solve this. So we're going to have to start with the law of cosines. And we're going to use that specifically to find H here. So we've got measurements for everything else here. So this becomes actually pretty simple here. We just solve that, and we get 73.4 feet for the distance from the pitcher's mound to first base here, significantly farther than the distance from the pitcher's mound to home plate. All right. Let's take a look at this one here. I'm going to block out myself here. In a softball game, a batter hits a ball to dead center field, a distance of 240 feet from home plate. The center fielder then throws the ball to third base and gets a runner out. The distance between the bases, again, is 60 feet. And how far is the center fielder from third base? So from this diagram right here, you can see that we have the following set of information from this. Since we know this is 45 degrees and all angles here in the diamond are 90 degrees, we can assume that this opposite side over here is 45. So here's the distance from home plate to third base. Here's the distance the batter hit the ball to direct center field, and here's the distance the ball traveled from the center fielder to the third baseman. So we've got three sets of information here. We're trying to find side A. This is side, angle, side. Once again, you're going to be using the law of cosines here. So take some time to solve this one. I'll be back in just a moment. Welcome back. Well, this made use of the law of cosines to solve for side A. Let's take a look at this here. What we did is we can write this equation here for A squared. And what we get is this, 202 feet. Remember, we have to take the square root of all of this stuff once we've calculated it in order to get our value for A. Okay, here's another application. Let me blank out myself here. A ship travels 60 miles due east and then adjusts its course as shown below. After traveling 80 miles in this new direction, the ship is 139 miles from its point of departure. That's to say, point of departure. Describe the bearing from point B to point C. Okay, so we've got this here, 60 miles, 80 miles, and we know that this third side here is 139 miles. We don't know any of the directions except that this initial one was due east. But can we figure out what the bearing is that this boat is now from point B to point C? Let's see if we can figure out what that is. Really, what we're finding is this angle right here, which we can figure out from this triangle by solving for angle B. What information do we have? We have all three sides. We don't have any angles. We need to use the law of cosines. So we're making use of this one because we want to solve for angle B. So we're going to have to solve this for the cosine of B. And we can do that by adding and subtracting things to either side here to get this term over here and the a squareds and c squareds and b squareds over here. Then divide off the 2ac here, so it's down here. And we can find out what cosine of b is. Let's just plug everything in, and we get this value confirming the fact that this is definitely an oblique angle right here. So let's find out what angle B is. It's 166 degrees here, and that means that we are traveling north, but 76 degrees east here. So this is, if we were to draw this, I don't think I have drawing capabilities here right now, but if we were to draw something due north, that would be a right angle with this over here. And so since the entirety of angle B is 166, if we subtract off 90 degrees from that, then the remaining part over here is 76 degrees. So the bearing that this boat is traveling is north, but 76 degrees east. Okay, so here's a similar problem to this. A ship travels 40 miles due east and then changes direction as shown in the figure. After traveling 30 miles in this new direction, the ship is 56 miles from its point of departure. Describe the bearing from point B to point C. So we're going here from point B to point C. We really need to know what this angle is right here so that we can describe the direction that this boat is moving alongside A here. We've got all three sides. We have no angles. You know what to do here. So take some time for this. I'll be back in just a bit. Welcome back. Well, once again, we're using the law of cosines here to find an angle. So it means solving it for the cosine value on one of those equations here. Specifically, we're looking at solving this for angle B here. So we would be using this version of the law of cosines so that we can solve for angle B here. So we do this, and we get this value here, indicating that angle B is oblique, which is reasonable considering what this picture looks like here. It looks like it's larger than 90 degrees. When we solve for angle B, we get 105.4 degrees, which means that if we consider north here to be 90 degrees from this side, let's subtract off 90 from this 105.4, and we get 15.4 degrees east of north. So this is going north 15 degrees east. Okay, and I also mentioned that you would be getting yet another formula for finding the area of a triangle here. This one comes from something called Heron's formula. Heron is a Greek mathematician from Alexandria, about 100 years BCE here. And this is the formula that he came up with. It's a very, very interesting formula where you calculate this thing called S, which is almost like the average of all three sides, except that you're not dividing it by 3, you're dividing it by 2. But you add all three sides together, divide by 2, and you get this value here, S. And the area of the triangle, as it turns out, is the square root of S times S minus A times S minus B times S minus C. This is Heron's formula for finding the area of a triangle. So this one is much like what we found before. It works on any triangle whatsoever. It doesn't involve the use of any trig functions whatsoever. So in some ways, it's even simpler to the ones that I was showing you with the law of sines. So interestingly enough. All right, so let's just use this here. So for any triangle, we can actually We've got three different sets of formulas for doing this here. The area of a triangle, as you learned in middle school, is 1/2 base times height. But the additional formulas that you learned earlier with the law of sines is 1/2 BC sine of A, 1/2 AC sine of B, 1/2 AB sine of C. And now we have this third formula here that is Heron's formula, which is the square root of s times s minus a times s minus b times s minus c, where s is equal to the three sides added together divided by 2. It's a good idea to have all three of these really listed in your cheat sheet somewhere. Okay, so let's use this here. It's going to be pretty straightforward on how we use this. Find the area of a triangle having sides of lengths this, this, and this. The only extra thing we have to find here is s. So we first of all find out what s is. S is 84. Okay. So then we just have to plug everything in to the formula here. This is 84 times 84 minus 43 times 84 minus 53 times 84 minus 72. And that gives us the square root of these four things being multiplied together, which gives us this. Very simple, very easy here. So I'm going to give you this formula here. You're finding the area of a triangle having sides of lengths 5, 9, and 8. Again, using Heron's formula. Take some time for that. I'll be back in a moment. Welcome back. Well, hopefully that was pretty straightforward based upon the stuff that we did just earlier here. Basically, just finding what S is. S in this case is 11. Plugging that into the formula, and you're getting this for an answer here, 19.9. Okay, so what are some things here that need to go onto your cheat sheet here? Fortunately, it's not like some of our previous sections here where you have a dozen different identities that have to be placed onto your cheat sheet. This is just the law of cosines in all three of its forms. You want to put that on there. Also, kind of understand what the pattern is between all three of those. Let's also make sure that we have Heron's formula stuck in there as well, so that you'll be able to use that. And then how do you use this to solve some real problems here? We really use the law of cosines when we're dealing with instances of side angle side or side side side. That's when we use the law of cosines. When we really do not have a combination angle opposite side where both of those things are known. That's when we really cannot use the law of sines. We need to use the law of cosines to, if for no other purpose, just to find one thing that will get us to the point where we can use the easier law of sines to find the rest of it. So hopefully that's helpful for all of you, and I will see you tomorrow.